If you would recall, last week we looked at what do we know so far, and we wanted to be able to start with a linear system, write down the augmented matrix, do row operations to find the reduced to echelon form, and then you use the reduced to echelon form to write the general solution to the linear system. Really, the emphasis is going to be on looking at the reduced to echelon form and deciding what that tells us, either about the linear system or relationships inside of a set of vectors, or relationships inside of a set of vectors that are being expressed as the columns of a matrix. So we want to add to this basic line by including, along with the linear system kind of on this end, we talk about a vector equation. I'm going to put that way over here on the left under linear system because we're going to take the vector equation and we are also going to turn that into an augmented matrix. We're going to write the vector equation as an augmented matrix. So in a sense, the vector equation is equivalent to some linear system. So there's a linear system related to the vector equation. It's a different way of expressing things. Once we have an augmented matrix, we want to look at the reduced to echelon form and then write the general solution to the vector equation. But then the thing we want to add to this end of our chain of events is the parametric vector form of the solution. So generally, if we have a vector equation, it's expressing a relationship between vectors, our answer should look like a bunch of vectors. So there's the parametric vector form of the solution. So the reduced to echelon form will also tell us how to write the parametric vector form of the solution. This was the thing that I didn't go over last week, but there was some DVD bonus material notes that talked about how to go from the general solution to the parametric vector form. In addition to all this, we want to add to this, the vector equation portion of things, the matrix equation. We want to take the matrix equation, which is equivalent to a vector equation, which is equivalent to a linear system. And the matrix equation will also get turned into an augmented matrix. We find the reduced to echelon form of the augmented matrix, and then we can write the general solution to the matrix equation, or more appropriately, their parametric vector form. The new framing that we have, even though vector equation and matrix equation are very closely related to linear systems, and it's really easy to see how these two equations lead to a system. We also want to introduce the language with vector equations and matrix equations of linear combinations. And so vector equations and and matrix equations will be answering questions like, is one vector a linear combination of other vectors? So in addition to all this, kind of before vector equations and matrix equations, we want to talk about linear combinations. And linear independence. Questions about linear combinations and linear independence will lead to vector equations and matrix equations. So these concerns will lead to matrix equations and vector equations, which lead to an augmented matrix, which will lead to a reduced to echelon form. And then that's how we answer questions with the reduced to echelon form. Right. One of the words that comes up when we're talking about linear combinations is span. So span is going to be, the span of a set of vectors is going to be also related to this linear combinations business. So here's the general picture of what we're working with. It all comes down to that basic maneuver we learned last week, the linear system to the augmented matrix, through row operations to the reduced to echelon form, to the general solution. We're just writing things in different ways. Any questions before we go on? So one thing I do want to go over, since we're all here now, is going from the general solution to the parametric vector form, because that's a connection that we'll need to make. We'll need to be able to go to from the general solution to the parametric vector form. So let's talk about that. Let's write down the general solution to a linear system. Oops. General solution to a linear system, and we're going to convert it to parametric vector form. We want to talk about how to convert the general solution to the parametric vector form. This is just another piece of the mechanical bit that we need in this class. We want to talk about the general solution to the parametric vector form. Let's suppose that we have some general solution to a linear system. I'm just going to make one up. Let's say x1 is -2 plus x3. Let's suppose that x2 is 3 minus, I'm going to change it up a little bit, 4x3, and that x3 is a free variable. One thing to note is that when you're writing the general solution to a linear system, you have to explicitly state what the free variables are. So if x3 is a free variable, you have to explicitly state that x3 is a free variable, even though you've implied that x3 is a free variable by writing x1 and x2 in terms of x3. The reason that I have you explicitly state that x3 is free rather than just implying that x3 is free is that I need to know that you know that we solve for the basic variables in terms of the free variables. Some of you wrote a general solution from the non-reduced row echelon form, and so you wrote x1 in terms of x2 as well. So x2 is a basic variable, so we don't want x1 in terms of x2. We want x1 and x2, the basic variables, in terms of just the free variables. So explicitly state what your free variables are. What we want to do is notice that there in x1 and x2, there are some constant values. And for x3, there are some coefficients of x3. We could think of this statement that x3 is free by writing an equation. We can think of the x3 is free by saying this equation is just saying that x3 is 0 constants plus 1 x3. And now we can see that x1, x2, and x3 is a linear combination of this constant, -2, 3, and 0, plus x3 times this vector, 1, -4, and 1. So I'm going to explicitly write the 1 in front of the x3. So we can write this as a single vector x. We can say the solution x looks like this constant vector, -2, 3, 0, plus x3 times the coefficients, 1, -4, and 1. Because we're reading x3 is free as x3 being 0 plus 1 x3. And so here is the parametric vector form. x3, the free variable, is the parameter in the parametric vector form name. What we're doing is we're taking our general solution and writing in the form y equals b plus m times x. Any questions? So we're really looking at this, thinking of this as a linear equation where y equals b plus m times x. A lot of times that's written as y equals mx plus b because I hate that form. I usually write the x on the other side, but I came from a tradition in linear algebra where the x3 got written in front of the vectors, and so I pass that weirdness on to you. Any questions? So if someone makes fun of you for writing your parameters in front of your vectors instead of on the other side, like mx, because this is kind of like the constant, the slope, the direction, and this is where it starts. So if someone be making fun of you for putting the x3 on the left instead of the right, just blame me. It's like, oh, Professor Leach made us do it this way. Even though I'm totally not making you do it that way, you can just accuse me of forcing you to write it that way. And then people will think, oh, that Leach, man, he's some kind of weirdo. Any questions? That's thing number one, going from the general solution to the parametric vector form. And then reading the parametric vector form. This is why we care about the parametric vector form, because what it is just a linear equation. It's a starting place, some constant, and then doing the same thing over and over again. Start at B and add M a bunch of times. That's all we're saying down here. Start with B, start at B, and then add M a bunch of times. Start with B and add M a bunch of times. That's all that's going on in this. That's all y equals mx plus b is. This is, after all, linear algebra. This is linear algebra, so everything should come out linear. If there was an x4 that was also free, then x1 and x2 would also have x4s in them, and then I would have two parameters. That's a good question. Let's do an example of that. Let's write down a general solution. Let's write down another general solution. Let's say we had -2 plus 1x3. And let's say we had a second free variable. Suppose we had a second free variable. Let's say minus 5x4. And then x2 was the same 3 minus 4x3. Let's suppose that x2 had nothing to do with x4. That came out, so it was 0x4. And let's suppose that x3 is free and x4 is also free. So in this case, I'm going to have a vector for the constants, a vector for x3, and a vector for x4. I'm going to read these second two lines. This is not part of the general solution, but I'm going to read x3 as x3 is 0 plus 1x3 and 0x4. x3 can't be written in terms of x4 because they're both free variables. And then here we also have an x4. So x4 is going to be 0, there's no constant, has nothing to do with x3, and has 1 to do with x4, because x4 is just equal to x4. So now, my parametric vector form, let's see, I'm going to write, say, x, I'm going to summarize it as one vector. I'll have the constant is just -2, 3, 0, 0. There'll be a vector for x3, and the coefficients of x3 are 1, -4, 1, and 0. And then there'll be a vector for x4. And the coefficients of x4 are -5. We can read this as x2 has 0 to do with x4. So the coefficients for x4 are -5, 0, x3 is 0, and x4 is 1. So this would be the parametric vector form if we had two free variables, x3 and x4. Any questions? All right. So this is related to some of your answers on the quiz. We looked at 4 columns, and I said this is we wrote an augmented matrix with 4 columns. An augmented matrix that has, with the 4 columns, is not going to have x4. If it's an augmented matrix, that rightmost column is the column for the constants. This is the 4th column. So if I had an augmented matrix where this was the solution, there's 4 variables and some constants, it would have 5 columns in it. Any questions? So this is something that we would conclude, this solution here, where there's a constant, an x3, and an x4, this would come from a 4 by 5 augmented matrix. Any questions? Comments? Snide remarks? Great. So that's how to go from the general solution to the parametric vector form. We should mention, geometrically, since it's come up, and it just one thing just keeps leading to another. Since it's come up, when we look at this solution with its one free variable, we have a constant and x3 times this one vector. If we think of this geometrically, the constant is where the vector starts and there's one free variable. So geometrically, this solution set is a line. There's a -2, 3, 0. It goes through that vector, and then it goes in this direction, 1, -4, 1. So since there's one free variable, we have a one-dimensional solution set. Dimensions might not be the right thing to say, but it's close enough. That's a little lazy on my part. So this is a solution set that will be a line. The solution set for this new example, where there are two free variables, we have a constant plus two free variables, this solution set is going to be a plane, because it goes in, has two different directions. So this solution set will be a plane in R4. Pardon me. Any questions? So we always want to think about the geometry of the things that we're doing. All right. That's going from a general solution to a parametric vector form. Let's pause the video and so we could switch over to going over homework problems.